This section we're going to get started looking at correlations. Now, looking at a correlation, one of the things we need to keep in mind before we move into doing the analysis is thinking about the context of data. So notice that simple raw data, like this data table that I have over here for you, doesn't really tell you very much. What we need to know is the context of the data, how it was collected, who the data was collected on, and that helps us know what kind of analysis we're doing. So when we're looking at this, for example, what if this set of data were test grades from students before and after instruction? So what kind of test would this be? Well, this would be the paired samples t-test. Now, what if this data was a reasoning test sample for women and men? What kind of test would that be? That would be the independent samples t-test. And what if it's a math reasoning score of X and a starting salary of Y? It's going to be the Pearson correlation they're going to be starting and looking at today. So hopefully paying attention to this, keep in mind as you move forward that the context of the data, how it's collected, has a lot to do with how we then analyze it. So it's easy in stats classes to get caught up in doing just your computations. But keep in mind that the larger picture of statistics is making the many decisions that has to be made before you start plugging your data in and running your analyses. So we're looking here at a correlation and then a linear correlation. So a correlation means that the values of one variable are somehow related to values of the other variable or are associated with them. So there's some relationship between the two variables. A linear correlation, which is what we're going to be focusing on here, is when there's a correlation and the plotted points of the paired data result in a pattern that can be approximated by a straight line. So we've got a correlation, that's a relationship between any two variables, and a linear correlation, which we're going to focus on here, specifically means that the pattern of connections can be approximated with a straight line. So here, if you look at your book in the opening part, we should be able to go through and look at these different types of correlations, be able to tell me which type these are. So if we're looking here at these two different ones, refer back to your book and the examples and the explanation they give there to see if you can figure out which type of relationships you're looking at in each of these figures. So the one here on the left is a positive. So as one variable increases x, so does variable y. They're going up together or conversely going down together. The one on the right is a negative relationship. That means that as one variable is going up, in this case elevation, another variable is going down, in this case the mean annual temperature. So here when we're looking at these two, for example, here we have no correlation at all for our purple data, and here on the right we have a curvilinear relationship. So there is a relationship, but it is not linear. So the relationship between these two variables is, can not be told to us through doing the simple linear coefficients that we're going to be using, because those tell us only about linear relationships. So if I asked a software data to plot a correlation for this data, it would give me a line that would look somewhat like this. That looks like there's not really any relationship between the variables. Well, that's inaccurate. There is a relationship. As you can clearly see, there is a pattern. However, it is not a linear pattern. So this using a software program to plot a simple linear regression analysis for this particular data plot would lead me to the false conclusion that there's not a relationship when in fact there is a relationship. I've simply tried to plug it into the wrong description level. So this is why you always plot your data first. Always plot your data with correlation. I can't say this enough. Doesn't matter where you are or your profession. The best experts of all, you would still plot your data first to take a look at what you have in your data. Do not just trust your raw numbers from running your analyses. So those examples that we looked at previously were kind of a little bit more extreme correlations. Here's some ones that are much more likely from real life distributions. So you can see when you're looking at these, when you're working with real life data, it's not going to be neat, clean lines very often. This example we have here looking at combined a person's memory score and then their language complexity. Overall is a pretty good positive relationship, but it's still a good bit scattered. But that's pretty much what you get with real life, because there's a lot of other variables that would be affecting memory score or language complexity. So we get a good relationship there, but notice the spread is a little bit more. Here on the right-hand side, we have a good relationship here, what we're looking at with life expectancy and gross national product. So here, as the gross national product goes up, overall, we expect to see life expectancy to go up. As you can see with this particular data set, that actually holds pretty true up to a certain level, and then it pretty much evens out. So you have a pretty good line going up there in the left-hand part way up to about 1/3, and then after that, it levels out. But that's another example of very real-life data, what we see when we're plotting correlations.